Hey folks, we're going to start using our skills with definite integrals to do some really interesting things. It's going to be a little mind bending. I got to warn you, so just do the best you can. I'm hoping this video might come in, handy if I didn't make it clear in class. But we're going to graph 9 minus x squared, and it says something like this in the problem. We're going to take this region that's bounded in the first quadrant between y equals 9 minus x squared. So here's 9 up here. It's a downward opening parabola. Just, to get as much information as possible, it's going to hit over here at 3. And it did say it's bounded in the first quadrant. We're going to revolve it or rotate it about the y-axis. It says that in the problem. So in my opinion, the first thing I would try to do is reflect it over the line, just so that you could imagine the thing rotating or revolving about that axis. And then I would try to imagine what it looks like. So, we're going to have this base, this circular base down here. Okay. And then you wouldn't be able to see this part right back here. That'd be hidden. All right. And then I'd probably make this solid, because then it looks like, what part is hidden, what part can we see? And it might still be kind of difficult to view. So what I'm going to do is I'm going to show you what it looks like in a three-dimensional modeling tool like Rhino. Okay. So I put down my function 9 minus x squared into a program called Grasshopper, and it fit that curve onto Rhino. Then I'm going to take this guy and I'm going to revolve it around the y-axis. So I go revolve, and it says what's the axis that you're revolving it around. You can just pick a couple points on the y-axis, and then I want to go full circle around the object. Okay, so right now it doesn't look very good because we're in front view, or top view, excuse me, and I'm going to go over here to perspective view, and we can rotate this thing around. Kind of maybe looks like a bit of like a bullet or a nose cone to a rocket, something like that, right? And we want the volume of this thing. So if I go to Rhino and I say volume, right, it's going to calculate it for me. But we're trying to figure out, like, how do you do this? So 127 cubic centimeters, if we're in centimeters, how do you do this with calculus? Okay. So hopefully I've made what the picture looks like, kind of like a bullet shape, right? And what we need to visualize, well, first, let me look back at my steps here. We're going to cut the solid into flat discs. So I'm still working on kind of guideline number one, is to take our shape and cut it into flat discs. But if it's difficult to imagine what it looks like, that cutting into flat discs is going to mean nothing at all. So Rhino has this cool command called contour. And contour does something like this. You select the object that you want to cut up, okay? And then you select the kind of like the axis that you're going to cut across, okay? And it says, well, how many cuts do you want to make? I'm going to make one every inch. Not how many cuts, but what distance between your cuts do you want? So if I go every 1 inch or 1 centimeter, it'll give me 9 cuts, okay? So we'll take one, the default. I hit enter, and it cuts them up. Now I can take those little cuts that it just made, and I can move them out of the shape. So each one of the cuts is going to be a circle. I hope you can see that. All right. So let me go back over to my guidelines. It says cut solid into flat slices. And I added this to their guidelines. The guidelines are on page 246, by the way. So I'll make that little note here on page 246. Okay. I think there's an important step here. We got to ID the slice, the cut. What solid did we just cut? Well, if we took one of these shapes and let's say we didn't go between like an inch or a centimeter, if we only went just like a millimeter up, so a tenth of what we just did here, if we only went just a tiny bit up, a millimeter up, then it would be a tiny little disc. Okay, so let me try to draw a tiny little disc in there and see if you agree with me. So instead of going a dramatic 1 centimeter up, we're only going to go a tiny little bit up. And then we would have this shape that, hopefully you agree with me, it would be a disc. And the height of our disc, this little chunk right here, is going to be dy. So that little thickness right there is dy. And we would need to identify what the radius is of our disk. And so I'm going to draw a radius in here, and I'm going to call that R. Now let me take this disk that I just drew, and like I was showing you over here, if we rotate it and just look at, like one perspective, we flatten it out, right? We would be looking at a circle. I think that makes life a little bit easier. So let me draw a circle over here. It doesn't have to be perfect. It doesn't have to be the same size as that one right there. That's not a very good circle, is it? And I'm going to draw my radius on there. Okay. So now it says, at the part where it says find the volume of this slice. Well, the volume of a cylinder, that's really what this is, a really, really short cylinder, would be the area of the base. So the area of this shape right here. So I'm trying to find the volume of this cross-sectional cut. I'll switch back to red so you know what I'm doing here. The volume is going to be the area of the base times the height, and the area of the base is this circle right here. So let me go pi r squared, and then the height of our cylinder is dy. Now, if I lost you between taking this, shape here and trying to draw it flat, you can't see the height of our cylinder here. So maybe if I took this cylinder over here and I gave it like a little bit more height than what is in that drawing over there, and then I gave it the base, and then I gave it a top, and I don't draw those little dash lines, maybe this will help. Okay. So what we have is just a really short cylinder. This is the height of my cylinder. This is the base of my cylinder. And to find the volume, you go base of the cylinder times the height of the cylinder. So I'm going to go pi r squared dy. That's the change in volume of this shape over here. So that's really my dv. When I put a dy in there for my height, it's really, now I'm saying I'm finding some change in my volume of my shape over here. I'm really not super happy with me putting a D down quite yet. Okay. So it's getting there. This is the volume of that one little cut right over there. That's the volume of that shape right there. Now I'm going to find the volume of the whole solid. So I'm going to go something like this. I'm going to go, the volume is equal to the integral. I'm going to add up infinitely many of these little cuts. So I'm going to go pi r squared dy. So now I found the volume of the slice. Here's the volume of the slice. And now I'm getting an equation. Oh, wait. Now I got to get an equation in terms of one variable. Wait. So see, this is R, obviously, and this is a Y. We got to have them all in the same variable. So I'm going to start adjusting this down here. I could adjust it here, right? So, I mean, technically I could say pi, let me switch back to red just so you know I'm still dealing with the little slice there. So I get pi times, now what is my radius? My radius is an x length. I come over here on the x-axis, right? So I could go pi x squared dy, but that's still not getting it. I want x in terms of y. So I'm going to have to solve this guy right up here for x. So I move my 9 to the other side. I don't think I have enough room up there. So I go y minus 9 is equal to negative x squared. I multiply everything by -1, so I get negative y plus 9 equals x squared. Then I'm going to take the square root of both sides. So I get the square root of negative y plus 9. Now, why in the heck did I do all that work? Because I can't have an x and a dy. I can't have an r and a dy in my integral. I'm going to have it all in terms of one variable. So I think I can do that right now. I'm going to substitute that guy in for x, and I would get pi times the square root of negative y plus 9 squared dy. Okay. Now, when we think about these slices, how much time do I have left? Okay, I got enough time. When I think about these slices, where was the biggest slice down here? This biggest circle is at the bottom, and then it gets a little bit small, a little bit small, a little bit smaller until it gets to the top, right? So we're slicing across the y-axis. So we want our limits of integration. This is really important. Listen to this. We want our limits of integration to go between 0 down here, between 0, the biggest slice would be down at the bottom, and the smallest one would be up here, 9, right? So I'm going to make my limits of integration 0 to 9, okay? So I hope I'm making that clear. Now, quite often with these antiderivatives, at least for these kind of beginner problems. This is the most difficult part, setting it up. The rest is, believe it or not, kind of easy. I can move the pi out front. I can write 0 to 9. And when you square a square root, they cancel out. So I've got negative y plus 9 dy. Now we're going to take the antiderivative. So I get pi times, let's see, that's going to be negative y squared over 2, and then plus 9y. And I want to evaluate it from 0 to 9. I'm going to kind of skip some of the arithmetic. And I ended up with 81 pi all over 2. Okay. That came out to be approximately, let's go back here and let's do the volume one more time. When I went to Desmos, it came out to be approximately 127.2 something or other. So this number right here was about 127.2. Let me actually jump over to Desmos real quick. I think I can do that without too much hassle. And I'll show you my calculation over there just so that you believe me. I got 127.234 something or other, right? So I guess I'd round it to 235. So 127.235 is my final answer. Okay. Cubic centimeters, since we're talking about a volume, and I had set Desmos up in terms of centimeters. So I guess it would be like units cubed if they didn't tell us, right? So units cubed. That's important in these problems because we are finding a volume. We're not finding some application of the integral for something else. Okay. That's the basics right there. I hope you're okay with that and that made sense. I appreciate you watching my video.